For decades, scientists believed they had a solid grasp on the vastness of the universe. It was undeniably large, but still seemed measurable, about 14 billion light-years across in every direction, home to a few 100 billion galaxies. This image, although awe-inspiring, felt like something that could be defined, something with a limit. Yet, when the James Webb Space Telescope shifted its gaze toward what appeared to be the deepest corners of cosmic emptiness, everything changed. The certainty of the universe's size and our place in it collapsed. Webb revealed a reality far beyond what we ever imagined, an observable universe nearly 93 billion light-years across, filled with galaxies, stars, and black holes hiding in places where no one expected them to be. But the deepest mystery Webb uncovered was not just how far we can now see. It's what lies beyond the cosmic horizon. What Webb showed us might be forever unreachable. With every breathtaking discovery, questions emerged. Questions that challenge everything we once thought was true about the universe's limits. The very nature of space itself began to unravel. To understand what Webb's findings truly mean, we first need to forget everything we thought we knew about how we observe space. For millennia, we assumed that space was simply a vast stretch of emptiness between stars, something we could look across. But space is more than just distance. It's deeply intertwined with time. It's the perfect marriage of the two that defines what we call the observable universe. Light moves at a constant speed, about 186,000 miles per second, fast enough to circle Earth 7 times in a single second. Yet even at that speed, distance turns into delay. The farther light travels, the older the image it brings when it finally reaches us. The farther we look into space, the more ancient the images we receive. A star just a few miles away from Earth has taken only a few millionths of a second to reach us. But when we look at the moon, we are looking 8 seconds into the past. The sun we see in the sky is not the sun of the present moment, but a version of it 8 minutes ago. This delay, while negligible on the scales of our daily lives, becomes staggering as we look farther into the depths of space. The light we see from stars in distant galaxies is not fresh, it's old, sometimes billions of years old. The farther we peer, the more ancient the light becomes. The night sky is not a live broadcast of cosmic events unfolding right now. It's an archive, a record of the universe's past. What Webb's discoveries have revealed is that the universe is not a snapshot frozen in time. It's a living, ever-shifting archive. Every point of light we see in the sky, every photon from every distant star, carries a timestamp, an imprint of time, of when that photon was born. And the farther away the galaxy, the older the message it carries. The universe is an unfolding story, but when we look at distant galaxies, we are witnessing not the present, but moments from billions of years ago still making their way toward Earth. But here's where the story turns even more strange. The universe does not preserve these messages intact. As the universe expands, the very fabric of space itself stretches, carrying galaxies apart from one another. When this happens, the light traveling through space gets stretched along with it. This is known as redshift. Redshift is more than just a visual change. It's the universe's way of saying, I've been expanding since this light was first emitted. The more stretched the light, the longer it has traveled, and the further back in time it was released. As space stretches, light does too, shifting from the higher energy blue and ultraviolet wavelengths into longer, redder infrared wavelengths. This stretch doesn't just make galaxies appear farther away, it's a record, a cosmic clock, marking how much the universe has expanded since the light was emitted. This principle, however, holds a deeper significance. For decades, astronomers worked with instruments designed to capture visible light, the same range of light that human eyes are naturally adapted to see. Telescopes like the Hubble Space Telescope revolutionized our understanding of galaxies and star formation by observing them through visible and ultraviolet light. But as the universe aged, and as astronomers attempted to peer further back in time, the galaxies began to fade, not because they were no longer there, but because the light from these ancient galaxies had shifted beyond the detection capabilities of telescopes like Hubble. The universe was becoming invisible to our instruments, and we were losing touch with its deep past. This is where James Webb comes in. Webb was specifically designed to capture this lost light, the infrared light that slipped past us for so long. Webb's massive mirror spans more than 25 feet and is coated in a thin layer of gold, an element chosen specifically because it reflects infrared light with incredible efficiency. Positioned nearly 1 million miles away from Earth, Webb can observe the universe with unparalleled clarity and detail. Webb's distance from Earth means it stays incredibly cold, and its temperature is essential to its function. Infrared light is directly tied to heat, and any warmth would overwhelm Webb's ability to detect faint, distant galaxies. It had to be a telescope so quiet and cold that it could hear the universe whisper. When Webb looks into what we once thought was empty, it's not seeking emptiness at all, it's waiting. It's waiting for the faintest of signals. Photons that have been traveling through space for 13 billion years. It takes hours, days, even longer for Webb to collect this ancient light, slowly gathering photons that have traveled through time and space from galaxies long gone. But what Webb found in that ancient light shattered expectations. It didn't find a young, fragile universe still struggling to form stars. Instead, it found fully formed galaxies, galaxies already bustling with activity. Massive, bright, and brimming with stars. These galaxies were far more advanced than models predicted they should be. Some galaxies were already producing stars at unprecedented rates. They were so luminous that Webb could detect them despite their vast distances. And the most shocking part? These galaxies existed when the universe was only 300 million years old, less than 3% of its current age. For astronomers, this discovery turned everything upside down. They had expected the early universe to be dim, slow, and evolving at a measured pace. Instead, Webb revealed a universe that was accelerating toward complexity. Galaxies were already massive, already mature in terms of star formation, and already creating heavier elements like carbon, oxygen, and nitrogen, elements that didn't exist in the early moments of the Big Bang. These elements forged inside stars were supposed to come much later, but Webb was seeing them in galaxies that existed far earlier than predicted. This wasn't just a surprising discovery, it was a paradox. The universe didn't wait patiently to evolve, it rushed. It assembled complex galaxies and stars in a fraction of the time scientists believed was possible. What does this mean for our understanding of the universe's origins? And if the universe could form so quickly, what does that say about its true size and complexity beyond what we can see? The discovery of the James Webb Space Telescope brought with it a flood of revelations, each more surprising than the last. What Webb uncovered was not a universe that was quietly assembling itself as once believed. Instead, what it found was an accelerated birth of complexity, where the universe rushed towards star formation, galaxy assembly, and black hole creation at a speed that defied all expectations. One of the most startling findings was the presence of supermassive black holes in the early universe. These black holes, some of them with masses reaching into the billions of solar masses, were not supposed to exist in such a young cosmos. According to established theory, black holes formed as a result of massive stars collapsing upon themselves, taking millions, even billions of years to amass enough mass to become supermassive. Yet, what Webb found was extraordinary. Supermassive black holes existed when the universe was only around 500 million years old, barely 5% of its current age. This discovery forced scientists to rethink their entire model of black hole formation. How could these gargantuan entities form so quickly, especially when the universe was still in its infancy? The conventional path to a supermassive black hole involves long periods of growth. First, stars form, live out their life cycles, and then collapse into black holes. But this process, slow and drawn out, doesn't explain how black holes could have reached such massive sizes so early in the universe's timeline. Some astronomers speculated that these black holes could have bypassed the usual path and formed directly from massive gas clouds, skipping the intermediate star stage altogether. This would allow them to grow more rapidly than the stellar collapse model would predict. Others suggested that direct collapse from even larger initial clouds could have occurred, much larger than anything we currently see today. Alternatively, black hole mergers could have played a crucial role in their rapid growth. In the early universe, galaxies were closer together, and galaxy mergers were far more common. These collisions could have brought together matter from multiple black holes, allowing them to grow more quickly than expected. These are theories that have yet to be confirmed, but the discovery itself has left astronomers questioning how black holes really come into being. The implications of these early black holes are vast. Not only do they challenge our understanding of black hole formation, but they also offer clues about the role black holes play in the broader structure of the universe. Supermassive black holes can influence their galaxies by dictating star formation, controlling the movement of matter, and even shaping the evolution of galaxies over time. Their presence in the early universe suggests that they played a larger role in cosmic evolution than we had previously thought. As Webb continued to reveal more distant galaxies, it became increasingly clear that the universe's early evolution was anything but calm and slow. Instead of galaxies creeping toward formation, we saw evidence of rapid and chaotic growth. Galaxies formed and merged quickly. Stars ignited with extraordinary speed. And black holes grew faster than anything in our previous models could account for. The most disorienting aspect of these findings, however, wasn't just the early formation of massive black holes. It was the chemical maturity of the early universe. Webb's instruments detected heavy elements like carbon, oxygen, and nitrogen in galaxies that were less than 500 million years old. These elements, which are critical for the formation of planets and life as we know it, do not appear in significant amounts in the universe's earliest stages. Their presence in these galaxies suggests that an earlier generation of stars had already lived, exploded, and enriched the universe with the materials necessary for the creation of more complex structures. This discovery is like finding finished buildings in a city that was supposed to be in the midst of construction. In the early universe, scientists expected only raw materials, gas and hydrogen, slowly coming together. What Webb revealed instead were galaxies with elements forged by multiple generations of stars. The universe was not patiently assembling, it was rushing towards complexity. The question was not just how galaxies formed so early, but why they were so mature, containing the essential building blocks of life so soon after the Big Bang. As astronomers revisited their models, the realization grew stronger. The universe had accelerated its own evolution. Galaxies that should have been small, fragile objects in a young universe turned out to be bright, massive, and teeming with activity. The cosmic clock, once thought to tick slowly, was racing backward. The universe wasn't gradually learning to build stars and galaxies, it was rapidly jumping towards maturity. One particularly perplexing aspect of Webb's findings was the sheer intensity of star formation in these early galaxies. Normally, star formation is a relatively inefficient process, with much of the gas inside galaxies never coalescing into stars. However, the early galaxies Webb detected were forming stars at a rate far greater than expected, creating immense numbers of stars in much less time than conventional models had predicted. The amount of light these galaxies emitted, bright enough to be detected from billions of light years away, implied that these galaxies had already accumulated enough mass to forge heavy elements and build the structures that would become the building blocks of even more complex systems. The intense formation of stars and galaxies at such an early stage also speaks to the dense nature of the early universe. Gravity was pulling matter together faster than expected, possibly due to the higher concentration of gas and dark matter. In the early universe, the density of matter may have been greater, allowing for faster star formation and the quicker assembly of large, massive galaxies. This dense environment could have created the perfect conditions for galaxies to form, grow, and collide with one another, leading to the rapid acceleration of the universe's evolution. Yet, even with all this incredible complexity unfolding at a rapid pace, there was one element of the early universe that still defied expectations: the cosmic web. The web-like structure that scientists had predicted was already present in the early universe, forming filaments of matter that stretched across vast distances. Webb's ability to observe these structures in detail has provided astronomers with new insights into how dark matter and gravity have shaped the universe's large-scale structure. Webb has mapped out the intricate pathways of matter and energy that connect galaxies across the cosmos, revealing a network of filaments and clusters stretching through space like a vast web of interconnected stars, galaxies, and dark matter. This web is more than just a theoretical construct. It's a real physical structure, one that Webb's instruments are capturing in unprecedented detail. By revealing how these filaments have connected galaxies and clusters over billions of years, Webb has helped us understand how the universe's most massive and complex structures came to be. These filaments are not just random collections of galaxies, they are pathways through which matter flows, channels through which galaxies grow and evolve. Webb's discoveries don't just change our understanding of the early universe, they also open up new questions about what comes next. If the universe accelerated toward complexity so quickly, what does that mean for the future of cosmic evolution? How much more massive and organized will the universe become in the coming billions of years? And perhaps most importantly, what lies beyond our observable horizon? As Webb continues to push the boundaries of what we can see, the answers to these questions are unfolding before us in real time. And with each discovery, we get closer to understanding the true scale of the universe we inhabit. As the James Webb Space Telescope peers deeper into the cosmos, it's not only revealing a more complex universe than we ever thought possible, but also a universe that defies the models and assumptions that have guided our understanding for decades. The universe, once thought to be a slow-moving, chaotic place, is showing us that it has always been more structured, more organized, and more active than we could have imagined. One of the most profound implications of Webb's observations is the sheer density of galaxies that were already present in the early universe. These were not small, fragile systems struggling to form. Instead, Webb revealed galaxies that were already massive, bright, and actively forming stars at intense rates. Some of these galaxies were emitting enormous amounts of light, so much so that even from the incredible distances Webb observed, we could still detect them. And these galaxies were forming when the universe was only about 300 million years old, a blink of the eye in cosmic terms. This early brightness was completely unexpected. The universe, according to long-standing theories, should have been much dimmer in its early years. The first galaxies, which formed after the Big Bang, were supposed to be small, fragile, and slow to develop. Yet Webb's findings show that these galaxies were already massive, capable of forming stars at rates comparable to much later galaxies. The universe wasn't just a patchwork of slowly evolving matter, it was actively creating galaxies, stars, and structures far more quickly than expected. And these galaxies were not just randomly scattered throughout the universe, they were part of a larger, organized structure that began to form much earlier than anyone could have anticipated. Webb's observations have confirmed that the cosmic web was already present when the universe was only a few billion years old. This web-like structure, composed of massive filaments of dark matter and galaxies, was responsible for shaping the very framework of the universe. It's a structure that continues to grow and evolve, one that connects galaxies, clusters, and vast voids across the cosmos. But what makes these discoveries even more astonishing is that they challenge one of the most fundamental assumptions about the early universe. For decades, scientists believed that the universe was spread out and lacked any real structure in its early moments. The idea was that the universe would have been a more uniform and homogeneous place, with only the faintest fluctuations in matter. These fluctuations would eventually have become the galaxies, stars, and other structures we observe today. The process was expected to be slow, with gravity gradually pulling matter together to form the galaxies we know. Webb, however, has shown that this was never the case. Instead of a uniform and quiet universe, it found a universe that was already dense with matter, organized into filaments and clusters. These structures were large and complex, forming at a speed that defies our previous models. What was once thought to be a slow process was in fact a rapidly accelerating one. The universe did not take its time. It was in a rush to create galaxies, stars, and black holes, and it did so with an intensity that challenges our most basic assumptions. Perhaps the most stunning aspect of Webb's findings is how early galaxies seem to have already undergone several cycles of stellar evolution. Stars are born, live, and die, and when they die, they release heavier elements into the surrounding gas, enriching the environment and allowing for the formation of new, more complex stars. Webb has detected these heavy elements, such as carbon, oxygen, and nitrogen, in galaxies that were formed only a few 100 million years after the Big Bang. These elements are forged in the cores of stars, and their presence in such young galaxies means that earlier generations of stars must have already formed, lived out their lives, and enriched the universe with the building blocks necessary for future star and planet formation. This discovery goes against the grain of what was expected. The first stars, known as population 3 stars, were supposed to be composed almost entirely of hydrogen and helium, the two lightest elements in the universe. These early stars were thought to be massive and short-lived, burning through their fuel quickly and exploding in supernovae. The explosion would have produced heavier elements, but this process was expected to take hundreds of millions of years. Yet Webb's observations show that the elements necessary for life, like carbon and oxygen, were already present much sooner than anticipated, indicating that the early universe underwent several cycles of stellar birth and death in a much shorter time frame than previously imagined. This raises a profound question. If the universe could form galaxies, stars, and black holes so quickly, what else could it have done in that time? What else is out there, hidden beyond the reaches of our current observation? The universe, it seems, was not only more efficient than we thought, it was more dynamic, accelerating toward complexity at a pace that left traditional models behind. As astronomers continue to analyze the data from Webb, they are left with a growing sense of awe and mystery. The early universe was not just a place where galaxies formed at a slow pace. It was a bustling, energetic place where massive structures grew rapidly and stars ignited with incredible speed. This revelation changes everything we thought we knew about the universe's beginning and its evolution. One of the most mind-bending aspects of this is the discovery of supermassive black holes. Webb detected these enormous entities in galaxies that were still in their infancy, existing when the universe was just a few 100 million years old. These black holes, each containing the mass of billions of suns, should not have existed at that time according to conventional theories. Black holes typically formed from the collapse of large stars, but it would have taken a long time for black holes to amass such enormous masses. And yet, there they were, supermassive black holes growing at a rate that completely defies our understanding of how these entities form. Astronomers are still debating the mechanisms behind their formation. Could these black holes have formed directly from gas clouds, bypassing the typical stellar collapse process? Could the first stars have been far more massive than we imagined, collapsing directly into black holes instead of going through their usual life cycle? Or perhaps black hole mergers were far more frequent in the dense early universe, allowing them to grow rapidly through the merging of smaller black holes. Each of these possibilities raises more questions than it answers. But what Webb's discovery makes clear is that the early universe was far more complicated, dense, and active than we ever thought possible. Webb's observations also shed new light on the cosmic web, the vast network of filaments that connects galaxies across the universe. This web is not just a theoretical construct, it's a real observable structure, one that Webb is revealing in exquisite detail. The cosmic web is made up of dark matter, galaxies, and gas, and it stretches across vast distances. Webb's ability to peer deeper into the cosmos has shown that these filaments were already well established when the universe was just a few billion years old, allowing matter to flow along them into growing galaxy clusters. The cosmic web is not just an abstract idea, it's a blueprint for how the universe grew and evolved. What makes Webb's findings even more extraordinary is that it has allowed us to see not only the visible structures in the universe, but also the invisible forces that shape them. By observing distant galaxies and analyzing the light from these faraway stars, Webb is giving us a glimpse into the dark matter that governs the universe's formation. These filaments of dark matter are the skeleton that holds everything together. Without dark matter, galaxies would not have formed, and the structure of the universe would have been completely different. Webb's discoveries are forcing us to confront the fact that the universe is vastly more complex than we imagined. The cosmos is not a random, chaotic place, but one with deep structure where matter flows along invisible paths, guided by forces we can't yet fully comprehend. Webb is not just showing us the universe as it is today, it is showing us the universe as it has always been, a place of incredible order, energy, and hidden potential. As the James Webb Space Telescope continues its unparalleled observations of the distant universe, it is revealing more than just galaxies and stars. Webb is uncovering the very forces that shape the structure of the cosmos, forces we have only begun to understand. The cosmic web that Webb has revealed is not just a theoretical construct, but a real, living structure that connects galaxies across the universe, dictating their formation and movement in ways that challenge our basic assumptions about how the universe evolves. The cosmic web is made up of vast filaments of dark matter, stretching for hundreds of millions of light years, and it connects galaxy clusters and voids, forming an intricate lattice across the universe. This web is not random. It is a structured network that has shaped the development of galaxies since the early days of the universe. Webb has confirmed that these filaments of dark matter and gas were already well established when the universe was just a few billion years old, making it possible for galaxies to form and grow rapidly. Webb's instruments have allowed astronomers to observe these filaments in unprecedented detail, showing how galaxies are not isolated entities, but part of a vast, interconnected structure. The light from distant galaxies travels along these cosmic highways, and Webb is capturing these signals as they make their way through space, revealing the universe's underlying architecture. One of the most fascinating aspects of the cosmic web is that it's not just the visible matter that shapes the universe. The dark matter that makes up most of the mass in the universe is invisible to traditional telescopes, but it exerts a profound gravitational influence. It is through the gravitational pull of dark matter that galaxies and clusters of galaxies are held together, forming the backbone of the universe. Without dark matter, the universe would be a much more random and disconnected place. What Webb's observations have shown is that the cosmic web is not just a passive framework. It is a dynamic system that is still evolving. As galaxies move along these cosmic filaments, they collide, merge, and form new structures. This process is not slow or gradual. It is a rapid and violent process. The early universe was far more energetic than we ever imagined, and Webb is revealing the chaotic, high-energy processes that were happening early on, much sooner than we expected. One of the most surprising findings from Webb's data is how early galaxies were already part of the cosmic web. These galaxies, which formed when the universe was still in its infancy, were already moving along the cosmic filaments, clustering together and interacting with one another. The process of galaxy formation, once thought to be a slow and deliberate affair, was in fact a high-speed race, with galaxies colliding and merging in a frenzy of activity. This high-speed formation of galaxies challenges our previous understanding of the universe's evolution. We had long assumed that galaxies formed slowly, with stars and gas slowly coming together to create the galaxies we see today. But Webb's findings suggest that the universe was far more efficient than we ever realized. Galaxies didn't just form, they were created and shaped by the gravitational pull of dark matter, interacting with one another and growing rapidly. As Webb continues to reveal more of the cosmic web, it's becoming increasingly clear that the universe is not just expanding, it is growing in a highly organized and dynamic way. The cosmic web is the scaffolding of the universe, holding everything together and driving the formation of galaxies and clusters. But it's also a living, evolving system, one that continues to change and grow, driven by the invisible forces of dark matter and dark energy. The more we learn about the cosmic web, the more we realize that it is not just a passive structure, it is the active engine of the universe. It is through the cosmic web that galaxies form, interact, and grow. And it is through this web that the universe's structure continues to evolve, with new galaxies and clusters being born from the cosmic filaments that stretch across space. Webb's ability to observe this cosmic growth in real time is offering us a glimpse into the dynamics of the universe as it was billions of years ago, and how it continues to evolve today. But Webb's discoveries are not just about understanding the large-scale structure of the universe, they are also shedding light on the dark matter that holds it all together. Dark matter, which accounts for about 85% of the universe's mass, is invisible to traditional telescopes, but its gravitational influence is impossible to ignore. Webb's ability to map the distribution of dark matter and reveal its role in shaping the universe's structure is helping astronomers unlock the mysteries of this invisible force. By analyzing the light from distant galaxies, Webb is detecting subtle distortions in the light caused by the gravitational pull of dark matter. These distortions, known as gravitational lensing, reveal the hidden mass that exists between us and the distant galaxies. Webb is using this technique to map the distribution of dark matter and track how it has shaped the formation of galaxies and clusters over time. What Webb has shown us is that dark matter is not a static entity. It is a dynamic force that has been shaping the universe since its earliest moments. Dark matter has created the framework within which galaxies and clusters have formed, and it continues to shape the evolution of the universe as it expands. But Webb's findings go beyond just mapping dark matter. The data is revealing that dark matter is also interacting with the gas and matter within galaxies, influencing how galaxies grow and evolve. This interaction between dark matter and visible matter is crucial to understanding how galaxies form and why some galaxies grow faster than others. Webb's ability to observe these interactions is giving astronomers a new understanding of the fundamental forces that govern the universe. As we continue to look deeper into the cosmos with Webb, it's becoming clear that the universe is far more structured and organized than we ever imagined. The cosmic web is not just a passive network of galaxies, it is a dynamic, living system that is constantly evolving. It is the backbone of the universe, shaping the formation of galaxies, clusters, and the very fabric of space itself. Webb's findings are helping us understand the hidden forces that govern this vast and mysterious structure. Yet even with all the incredible discoveries Webb has made, there is still so much left to uncover. The mystery of dark matter, the formation of supermassive black holes, and the nature of dark energy are still questions that remain unanswered. But as Webb continues to push the boundaries of our understanding, it is revealing a universe that is far more complex, dynamic, and interconnected than we ever realized. The more we learn, the more we see just how much is out there, waiting to be discovered. As the James Webb Space Telescope continues its mission to peer further into the cosmos, it is exposing a universe that is not only more dynamic and active than previously imagined, but also one that is governed by forces that we cannot see, touch, or fully comprehend. The vast structures Webb has revealed are not just the remnants of an ancient universe. They are part of a living and breathing system, one that continues to evolve under the influence of invisible forces. One of the most profound insights Webb has provided is its ability to map out the large-scale structure of the universe, the cosmic web, which stretches across vast distances, connecting galaxies in filaments that reach across hundreds of millions of light-years. This intricate web is not just a network of matter scattered randomly in space. It is a structure shaped by the forces of gravity and dark matter that govern the universe. These invisible forces are responsible for guiding the formation of galaxies and clusters, ensuring that the universe doesn't just exist in a chaotic, random way, but instead follows a precise and organized pattern. Webb's observations have given us a glimpse into how these cosmic filaments were already well established when the universe was still in its early stages, just a few billion years old. This has profound implications for our understanding of the evolution of the universe. We once thought that the early universe was a chaotic, disordered place, where galaxies slowly formed in an isolated manner, eventually coming together to form larger structures. But Webb has shown us that the universe's structure was already in place much earlier than we had thought, and matter was flowing along these filaments, joining together into massive clusters of galaxies. The cosmic web is an extraordinary example of structure in the universe, but it is also a reminder of just how much of the universe remains hidden from our eyes. While Webb's advanced infrared instruments have provided us with a glimpse into the early universe, much of what we see is just the surface of a deeper, unobservable reality. The cosmic horizon, the boundary of what we can observe, is not the end of the universe. It is merely the edge of what light can travel across, influenced by the rapid expansion of space. This expansion, driven by dark energy, stretches space at an ever-increasing rate, carrying galaxies and clusters away from each other. As light travels across space, it is stretched along with it, a process known as redshift, which stretches the wavelength of light toward the infrared spectrum, making distant objects harder to detect. Webb is capable of detecting this stretched light, allowing it to look deeper into the past than any telescope before it. But even Webb has its limits. The cosmic horizon represents the boundary of what we can see, the edge beyond which galaxies, stars, and black holes are hidden from us forever. As Webb peers deeper into the past, it begins to expose the early stages of cosmic evolution. The galaxies it has detected are not just faint glimmers in the distance, they are bright, massive, and active. These galaxies were forming stars at an accelerated rate, much faster than previously thought, and their early formation challenges the long-standing models of galaxy evolution. For a long time, astronomers believed that galaxies formed slowly in isolated pockets of gas and dust, but Webb's data shows that the universe was already full of luminous and mature galaxies that were creating stars at an extraordinary rate, far ahead of schedule. This rapid formation of galaxies has forced scientists to rethink the nature of star formation itself. The early universe was once thought to be a dim and quiet place, where stars were born slowly and their light gradually spread across the cosmos. But Webb has shown us that the universe didn't take its time, it rushed toward complexity. Galaxies that should have been small and fragile were already bright and massive, containing stars that formed at intense rates. This has far-reaching consequences for our understanding of the timeline of cosmic evolution. One of the most perplexing aspects of Webb's discoveries is the amount of heavy elements found in these early galaxies. Carbon, oxygen, and nitrogen, elements essential for life, were already present in these young galaxies, indicating that earlier generations of stars had already formed, lived, and died, enriching the universe with the elements necessary for future stars and planets. This raises a critical question. How could such complex elements form so early? The universe was supposed to be in its infancy, but Webb is showing us that it had already gone through multiple cycles of stellar birth and death, much sooner than we thought. This discovery is important, not only for understanding the evolution of galaxies, but also for understanding the origin of life. These heavy elements are the building blocks of the chemistry of life, the very elements that form planets, oceans, and the organic molecules that give rise to life itself. If the universe was already producing these elements so early, what does that say about the possibility of life elsewhere in the cosmos? Could life have emerged much earlier than we think? Or could it still be forming in parts of the universe that we cannot see? As Webb continues to uncover these mysteries, it becomes increasingly clear that the early universe was far more advanced and active than we could have imagined. But these discoveries also raise new questions about what lies beyond our current observations. The observable universe is only a fraction of the entire cosmos, and as Webb pushes the boundaries of what we can see, it forces us to confront the fact that much of the universe will remain forever hidden. One of the most profound realizations of Webb's discoveries is that the universe is far larger and more complex than we ever thought. The observable universe, once thought to be the totality of everything we can study, is now revealed to be just a small fraction of the whole. Beyond the cosmic horizon, galaxies, stars, and black holes continue to evolve, but they will never be visible to us. The universe is expanding at such a rapid pace that regions of space are being carried beyond our reach, leaving us to wonder what lies in the vast, unseen parts of the cosmos. The cosmic horizon is not a physical edge. It's the limit of what light can reach. As space continues to expand, more galaxies will slip beyond our observational reach. Webb can push the boundaries of what we can see, but even its remarkable capabilities cannot overcome the inherent limits imposed by the universe's expansion. The distant future will see galaxies beyond our cosmic horizon slowly slipping into invisibility, their light forever lost to us. As the James Webb Space Telescope continues to send back groundbreaking data, it becomes clear that the universe is not simply a vast expanse of stars and galaxies. Webb has revealed a universe that is far more dynamic, interconnected, and influenced by invisible forces than we ever imagined. It is a universe shaped not just by the visible matter we can observe, but by the forces of dark matter and dark energy, which govern the fabric of space-time itself. These discoveries force us to confront the limits of our understanding and the unknowns that remain in the deepest corners of the cosmos. As Webb has shown, the observable universe is much more crowded and structured than we once thought. But as we peer deeper into the cosmos, it becomes increasingly clear that the universe is constantly expanding and evolving in ways we are only beginning to understand. One of the most profound insights Webb has provided is the discovery of dark matter's central role in shaping the universe. This mysterious, invisible substance makes up about 85% of the matter in the universe, yet it has eluded direct detection for decades. Dark matter does not emit light, nor does it interact with normal matter in any detectable way, yet its gravitational influence is undeniable. Without dark matter, the structures we see in the universe, galaxies, clusters, the cosmic web, would not exist. Webb's ability to map out the distribution of dark matter has provided us with an unprecedented view of how this invisible substance shapes the structure of the universe. Through the technique of gravitational lensing, Webb is able to observe how light from distant galaxies is distorted by the gravitational pull of dark matter. These subtle distortions reveal the location and density of dark matter, which is scattered throughout the cosmic web, acting as the scaffolding that holds galaxies and clusters together. Dark matter is not just a passive force, it is actively shaping the evolution of the universe. It is through the influence of dark matter that galaxies were able to form in the first place, gathering gas and dust into dense regions where stars could ignite. Over billions of years, dark matter has played a crucial role in galaxy formation, and its gravitational influence continues to shape the motion and structure of galaxies, even today. Without dark matter, the universe as we know it would not exist. But while dark matter is an essential force in shaping the universe, it is not the only invisible force at play. Dark energy, which makes up about 68% of the universe, has a far more profound influence on the cosmos. Dark energy is the force that is causing the accelerating expansion of the universe, a discovery that revolutionized our understanding of cosmology in the late 1990s. Dark energy's presence has been felt in every corner of the universe. It is responsible for the fact that galaxies are moving away from us at an ever-increasing rate. The universe is stretching and growing at an accelerated pace, and dark energy is the driving force behind this expansion. Unlike dark matter, which clumps together and pulls matter in, dark energy pushes everything apart, accelerating the expansion of space and causing distant galaxies to slip beyond our reach. The discovery of dark energy changed everything. For most of the 20th century, scientists believed that the expansion of the universe was slowing down due to the pull of gravity. However, when astronomers observed distant supernovae in the late 1990s, they found that these stars were receding from us faster than expected. The universe wasn't slowing down, it was speeding up. This acceleration was caused by dark energy, a mysterious force that counteracts the gravitational pull of matter and drives the expansion of space. But as Webb continues to peer deeper into the universe, it is revealing the complicated relationship between dark matter and dark energy. These two forces seem to be at odds with each other, with dark energy pushes everything apart. This tension has created the universe we see today, one that is structured on small scales, with galaxies and clusters held together by dark matter, but one that is expanding and growing on the largest scales due to the influence of dark energy. The interplay between dark matter and dark energy raises a profound question. What will the future of the universe look like? The universe is expanding at an accelerating rate, and if dark energy continues to dominate, the universe will continue to grow forever. The distant galaxies we see today will slowly drift beyond our reach, and eventually the universe will become an empty, cold void, filled only with galaxies that are isolated and fading into the darkness. If dark energy remains constant, the universe will continue to expand for trillions of years, with galaxies becoming increasingly isolated. The day will come when the cosmic horizon, the boundary beyond which we cannot observe, will move so far away that even the distant galaxies we see today will be lost to us forever. In this scenario, the universe would continue to expand, but it would become lonely, with only a handful of galaxies remaining in contact with one another. However, there is still uncertainty surrounding dark energy's role in the universe's future. Some theories suggest that dark energy may not remain constant, but could change over time. If dark energy increases in strength, it could lead to an even more dramatic scenario, the Big Rip. In this scenario, dark energy would accelerate the expansion of the universe so rapidly that it would eventually tear apart galaxies, stars, planets, and even atoms themselves. The universe would be pulled apart at every scale, in a cataclysmic event that would mark the ultimate end of everything. While the Big Rip remains speculative, the implications of dark energy's influence are far-reaching. Even if the universe does not end in a Big Rip, it is clear that dark energy is shaping the universe's fate. The accelerating expansion of the universe means that the observable universe, the portion of the cosmos that we can see and study, will continue to shrink as galaxies slip beyond the cosmic horizon. The universe is not just expanding, it is slipping away from us, and there is nothing we can do to stop it. These revelations raise profound questions about the ultimate fate of the universe. Will the dark energy that is driving the expansion eventually bring about the end of the universe? Will we witness a future where the cosmic horizon becomes an impenetrable wall, beyond which no light can ever reach us? And more unsettlingly, if the universe continues to expand indefinitely, will it become a place of complete isolation, where galaxies and stars drift further and further apart, with no connection or communication between them? As Webb continues to look deeper into the universe, it forces us to confront these existential questions. The discoveries it has made are not just about uncovering the structure of the universe. They are about understanding where the universe is headed. The cosmic horizon is not just a limit to our observation. It is a boundary that defines the very nature of the universe itself. Beyond that horizon, there is a vast, unseen cosmos, one that is forever out of our reach. And as time goes on, more and more of the universe will slip beyond the cosmic horizon, leaving us with only the small fraction of the universe that we can see. As the James Webb Space Telescope delves deeper into the universe's distant reaches, its discoveries continue to push the boundaries of what we thought was possible. One of the most profound implications of Webb's observations is the revelation that while the observable universe is vast, it is ultimately limited by forces we can neither see nor touch. Beyond the cosmic horizon, there exists a vast expanse that will remain hidden from us forever. This boundary, the limit of our observable universe, is not a physical edge, but a consequence of the expansion of space itself. As the universe expands at an ever-increasing rate, more and more galaxies, stars, and cosmic structures are moving beyond our reach. The light they emit can no longer reach us because space is stretching too fast, and as time moves forward, the gap between the observable universe and the unobservable reaches will continue to grow, making it impossible for us to ever witness the full extent of the cosmos. At first glance, the idea of the unobservable universe may seem like a distant theoretical curiosity. But as Webb's findings have shown, this is a reality we must confront. Even the extraordinary capabilities of Webb, the most advanced telescope ever built, can only reveal a small fraction of what exists in the cosmos. The light Webb detects has traveled across billions of years to reach us, but even this light is being stretched and diluted by the accelerating expansion of space. There are regions of the universe that have been forever cut off, never to be observed by us, regardless of how advanced our technology becomes. The concept of the cosmic horizon introduces a stark reality. The universe does not simply end at the edge of what we can observe, it continues beyond that point, in ways that will remain forever out of our reach. We used to think of the observable universe as a complete, finite thing, an all-encompassing cosmic picture that we could study and understand. But now we see that what we observe is just a small slice, a glimpse into a much larger reality. What does this mean for the future of cosmic exploration? As more galaxies slip beyond our observational reach, it becomes clear that there is a fundamental limit to what we can ever discover. We will continue to learn and explore, but there will always be an immense part of the universe that will remain hidden. This is the paradox of modern cosmology. The more we discover, the more we realize how much we will never know. As we try to comprehend the vastness of the universe, the question emerges, what lies beyond the cosmic horizon? The answer is tantalizing, but ultimately elusive. We know that beyond the observable universe, galaxies are still forming, stars are still burning, and black holes are still growing. The laws of physics as we understand them continue to apply. Yet, because space is expanding so rapidly, we will never be able to observe these regions, and we can never know how they evolve. The idea of an unobservable universe raises new questions about space-time and cosmic evolution. If there are galaxies and structures that are beyond our observational reach, then the universe we are witnessing is not the full picture. There is an entire expanse of reality that we will never experience. Some models suggest that the universe is infinite, extending far beyond the cosmic horizon, with structures and galaxies far more complex than anything we can imagine. But as Webb has shown, we will never be able to confirm this. The unknowns will remain unknown, hidden behind the vast expansion of space. The cosmic horizon is not a static boundary. As the universe continues to expand, the horizon shifts, moving farther away from us. This means that galaxies that we can observe today will eventually cross beyond the cosmic horizon, leaving us with only a handful of nearby galaxies to study. In the distant future, this expansion will make the universe feel increasingly isolated, with far fewer galaxies to observe. We may reach a point where only a few galaxy clusters remain visible, surrounded by a growing void of space. It's a sobering thought. The universe we see today will become more isolated and lonely over time, as more and more of it slips beyond our reach. Even if we can continue to observe the universe for billions of years, the accelerating expansion of space will ensure that we can never fully grasp the scale of what lies beyond our observable bubble. The universe will continue to grow, but as more regions fall out of our observational range, we will lose the ability to study the vast majority of what exists. The universe will keep evolving, but from our perspective, it will feel increasingly empty and incomplete. This realization raises a difficult question. If we cannot fully observe the universe, then what is the purpose of our cosmic exploration? The answer, perhaps, lies in the very nature of exploration itself. Even though we can never see everything the universe has to offer, our quest for knowledge is still invaluable. The discoveries we make today, the understanding we build, and the knowledge we gain will continue to shape the future of science and exploration. The universe may be far beyond our ability to fully understand, but what we do learn today can still have profound effects on the human experience. Webb's findings have already redefined our place in the cosmos, challenging our understanding of space, time, and cosmic evolution. Each new discovery brings us closer to answering the questions that have fascinated humanity for centuries. How did the universe begin? How did galaxies, stars, and planets form? Are we alone in this vast, expanding cosmos? While we may never have answers to all of these questions, the very act of asking and searching brings us closer to understanding our place in the universe. Exploration is not about finding all the answers, it's about embracing the unknown, and Webb has shown us just how much more there is to discover. As the universe expands, we will continue to push the limits of our understanding, but the cosmic horizon reminds us of the fundamental limits of observation. There will always be more out there, more galaxies, more stars, more structures that we will never see. And yet, what we can see is enough to transform our understanding of the cosmos. As the universe stretches further into the unknown, the James Webb Space Telescope continues to redefine our understanding of the cosmos. Webb has exposed a deeper, more complex universe than we ever thought possible, one that is not only vast but incredibly dynamic, with hidden forces at play that we are only just beginning to understand. However, the deeper we look, the more we confront a paradox that is both awe-inspiring and deeply unsettling. The more we discover, the more we realize just how much of the universe will forever remain out of reach. For centuries, humanity has gazed into the night sky, imagining what lies beyond the stars. As our tools have evolved, from the first telescopes to the most advanced space observatories, our knowledge of the cosmos has grown exponentially. Yet Webb has brought us to the edge of a new understanding, where the expansion of the universe itself presents us with a harsh reality. Much of the universe we strive to understand is already hidden from view, and as time moves on, it will become more so. The concept of the cosmic horizon has never been more tangible. It is the point beyond which light from distant galaxies cannot reach us, not because those galaxies no longer exist, but because the space between us and them is expanding faster than the speed of light. This is a direct consequence of dark energy, a mysterious force that is accelerating the expansion of the universe at an ever-increasing rate. This revelation has led to an unsettling realization. As time passes, the universe itself is slipping away from us. The galaxies we see today are already moving farther beyond our reach, and soon their light will no longer be able to reach us. The cosmic horizon is not just a boundary in space, it is a boundary in time. The light we observe from the most distant galaxies has been traveling for billions of years, offering us a glimpse of the universe as it was long ago. However, as the universe continues to expand, even the light we see today will become more and more stretched, eventually fading into redshift so extreme that no telescope, no matter how advanced, can detect it. The early galaxies that Webb has revealed, glowing brightly in their infancy, will eventually fade from view as their light shifts further into the infrared spectrum, beyond our ability to detect. This marks a profound shift in how we understand the cosmic scale. For most of modern astronomy, we assumed that the universe was a vast yet ultimately measurable thing. We had always thought of the universe as something that could, in theory, be comprehended, mapped, catalogued, and understood. The observable universe, once thought to be the limit of our knowledge, is now revealed to be just a fraction of what actually exists. And as the expansion of space accelerates, even that fraction will shrink, leaving us with an increasingly distant and isolated universe. The expanding horizon presents not only a scientific challenge, but also a philosophical one. If the universe is constantly growing and expanding beyond our reach, what does that say about the fate of human exploration? Will we, as a species, ever fully understand the universe? If so much of it is forever out of our grasp, can we truly claim to know the nature of the cosmos? Webb's discoveries have made it clear that the universe is vast beyond comprehension, and yet we are bound by the constraints of space and time. Even as our technology advances and our telescopes peer deeper into the past, the universe itself is outpacing our ability to explore it. This realization forces us to confront the limits of observation. Webb's ability to peer back in time and detect galaxies that formed billions of years ago is an incredible achievement, but it also serves as a reminder of the boundaries of our reach. However, this understanding does not diminish the importance of our exploration. Despite the cosmic horizon, the boundary beyond which we can never see, what Webb has revealed to us is nothing short of extraordinary. We have learned that the universe is full of structure, far more organized and complex than we ever thought possible. Galaxies form along vast filaments of dark matter, creating a cosmic web that stretches across the universe. And even though we may never observe the entirety of this structure, the very fact that we can now see its presence changes everything. It changes how we think about the universe's evolution, its beginning, and its future. Webb's discoveries challenge our assumptions about how the universe works. For so long, we believed that galaxies and stars formed in isolated pockets, slowly gathering matter and gradually evolving into the structures we see today. But Webb has shown us that the universe is not a quiet, slow-moving place. It is vibrant, active, and incredibly efficient. Galaxies form and merge at a pace that defies our expectations. Stars are born, live, and die in the blink of an eye in cosmic terms. This acceleration toward complexity challenges everything we thought we knew about cosmic evolution. What makes this realization even more humbling is the fact that we are observing these ancient objects as they were millions or billions of years ago. The light Webb captures has taken so long to reach us that we are witnessing the universe as it once was, not as it is. Every galaxy we observe is a snapshot of the past, an archive of cosmic history that has traveled across the vast expanses of space and time to reach us. But even this ancient light is not the full picture. As we look deeper into the cosmos, we encounter the cosmic horizon, beyond which light from distant objects will never reach us. This is the ultimate limit to our exploration. As much as we strive to understand the universe, there will always be a part of it that is forever hidden, beyond our observational reach. The observable universe is only a tiny sliver of the greater cosmos, and as we continue to observe, we are constantly reminded of how much more there is that we will never see. This limitation is not just a technical challenge, it is a philosophical one. If we can never fully comprehend the universe, what does that mean for our place in it? Are we simply observers of an endless expanding cosmos, unable to reach its farthest corners? Or does the very act of seeking, of exploring, give us purpose in a universe that is beyond our complete understanding? Despite these uncertainties, the discoveries made by Webb are a reminder of how much we have already accomplished. Through the power of technology, curiosity, and human ingenuity, we have unlocked the secrets of the universe's early years, from the formation of galaxies to the evolution of the cosmic web. And as we continue to explore, we may uncover even more mysteries that challenge our understanding and push the boundaries of what is possible. Yet, as the universe stretches beyond our observational reach, it leaves us with a final, haunting question. What lies beyond the cosmic horizon? Is there more to the universe than we can ever comprehend? Will future generations be able to see further than we ever could, or will they be limited by the same forces that restrict our view? The cosmic horizon is both a boundary and an invitation, a reminder of how much there is still to discover, even as we recognize the limits of our perception. It is a reminder that the universe is vast, and perhaps, just maybe, infinite, with more to explore than we could ever dream. As we peer deeper into the universe through the lens of the James Webb Space Telescope, one thing has become overwhelmingly clear. The universe is not just a vast static expanse, but a dynamic, evolving entity full of mystery and complexity. Webb has revealed a universe that challenges everything we thought we knew about cosmic evolution. Yet as we delve further, we realize that the most unsettling aspect of all is not just what we can see, but what we can never see. The cosmic horizon is not just a physical boundary, it's a reflection of our limitations as observers. While Webb has uncovered galaxies, stars, black holes, and cosmic structures that were once hidden in the far reaches of space, there will always be regions of the universe forever beyond our grasp. The idea that there is so much out there that we can never observe, no matter how advanced our technology becomes, forces us to confront the ultimate unknowns of the cosmos. What lies beyond this horizon? Are there other galaxies, more black holes, or even alien civilizations that exist just out of reach of our instruments? The truth is, we don't know. What Webb has shown us is that the universe is not just larger than we thought, it's far more complex and unpredictable than we could have imagined. There is an infinite amount of space, filled with the potential for more discovery, and yet so much of it will remain forever hidden from us. But as Webb continues to reveal the universe's early stages, it forces us to grapple with another question. What does it mean to observe? What does it mean to study a universe that is forever changing and moving beyond us? For much of our history, we believed that the universe was a static thing, a series of fixed points in space, a set of objects we could track and measure, and ultimately understand. But Webb's discoveries suggest that the universe is not just changing, it is constantly evolving, with galaxies forming, merging, and transforming at an astonishing pace. What this means is that the universe is far less like a finished puzzle and more like a fluid, ever-shifting work of art, constantly being reshaped by forces beyond our control or comprehension. The galaxies Webb sees today are not static objects frozen in time, they are active, vibrant systems that have lived and evolved and will continue to do so long after our instruments have ceased to function. Even as we discover new galaxies and cosmic structures, they are already in the process of changing. The universe, in a very real sense, is alive, not in the traditional sense of life, but in the sense that it is constantly moving, reshaping and reconfiguring itself in ways we can only begin to understand. This brings us back to the cosmic horizon, a boundary that is not fixed but dynamic. As the universe expands, the horizon itself expands, and the galaxies that are currently visible to us will eventually fade into invisibility. The light we are receiving from these galaxies today is not just a snapshot of the present, it is a glimpse into the past. When we observe the farthest galaxies, we are looking at moments in the universe's history that occurred billions of years ago, when stars were first born, galaxies were first forming, and the cosmos was still in its infancy. But as the universe continues to expand, even the light from these galaxies will become increasingly stretched and diluted, until it is no longer detectable by our instruments. This leads to a sobering realization. We are not just looking into the past when we observe the universe, we are also looking into a future that we can never witness. The galaxies that we see today will eventually drift beyond the cosmic horizon, and their light will fade away. The universe, for all its immensity, is also transitory, with an inevitable end looming in the far future. The implications of this are profound, not just for our understanding of space and time, but for our very place in the cosmos. If we cannot observe the future of the universe, then what can we know? What can we truly say about the nature of cosmic time and the forces that shape it? Webb's findings have shown us that the universe is far more dynamic and organized than we ever expected, but they have also reminded us that much of the universe will forever remain beyond our reach. The boundaries of observation are not just technical limits, they are a fundamental aspect of cosmic reality. We are not just observers, we are participants in an ongoing cosmic drama that is beyond comprehension. As we come to terms with the cosmic horizon and the limits of human observation, we are faced with an inevitable question. What does it mean to be human in such an immense, evolving, and mysterious universe? The universe has always been vast, but as we uncover more and more about its origins, its structure, and its future, we realize just how much we don't know. Yet even in the face of these unknowns, we continue to explore, to ask questions, and to seek answers. It is this curiosity, the desire to understand the cosmos, that drives us forward. The discoveries made by Webb have already reshaped our understanding of the universe, and they will continue to challenge us for decades to come. As we look deeper into the cosmos, we are forced to confront the limits of our knowledge. But that does not mean we stop searching. Instead, it means that the more we discover, the more we understand how much there is left to explore, how much is still hidden beyond the boundaries of our reach. In the end, the true beauty of cosmic exploration is not in the certainty of the answers we find, but in the infinite number of questions that remain. The universe is not just a static backdrop to our existence, it is a vast, ever-changing and mysterious place, full of surprises, wonders, and ultimately, unknowns. And perhaps that is the greatest discovery of all, that the journey of exploration is not about finding all the answers, but about embracing the mysteries that lie beyond. As the James Webb Space Telescope continues to uncover the deepest corners of the universe, it forces us to confront a crucial realization. No matter how advanced our technology becomes, we will never be able to fully understand the vastness of the cosmos. The deeper we look into the universe, the more we realize how much of it will always be out of reach, hidden from view by the very nature of space itself. Yet paradoxically, it is this very limitation that makes the pursuit of knowledge all the more compelling. The cosmic horizon, the point beyond which light from distant galaxies will never reach us, has become the defining feature of modern cosmology. Webb's ability to peer into the past, capturing the faint light of galaxies that formed when the universe was only a few 100 million years old, has revolutionized our understanding of cosmic history. But with this knowledge comes the sobering recognition that we will never be able to observe the entirety of the universe. Even as we discover more about the early stages of the universe, entire regions of space will remain permanently out of our reach, hidden behind the expanding fabric of space itself. What does this mean for the future of cosmic exploration? Will we continue to push the boundaries of observation, knowing that we can only glimpse a fraction of the universe's true scale? Or will the realization that much of the universe will forever remain hidden change the way we think about our place in the cosmos? Webb's discoveries have shown us that the universe is vast, but it is also dynamic, constantly evolving, and increasingly interconnected. As the telescope peers deeper into the past, it reveals a universe that was once thought to be chaotic and slow-moving, but is now revealed to be organized, efficient, and active. Galaxies that should have taken millions or billions of years to form are already bright, massive, and actively producing stars within the first few 100 million years after the Big Bang. Stars, galaxies, and black holes are not simply drifting through space. They are being shaped by invisible forces, like dark matter and dark energy, that we are only beginning to understand. Yet, even with these groundbreaking discoveries, Webb's findings raise a fundamental question: how much of the universe is truly knowable? Webb can look deeper into space than any telescope before it, yet even it has limits. The farther we peer into the cosmos, the more we realize that the universe is not just larger than we imagined, it is more complicated and mysterious than we could have ever predicted. As we continue to explore, we are forced to acknowledge that the unobservable universe, the regions beyond the cosmic horizon, will forever remain a mystery. For all our progress in understanding the early universe and the evolution of galaxies, there are vast regions of space where the light has been stretched beyond recognition, where galaxies will slowly drift beyond our reach, and where the laws of physics may play out in ways we can never observe. This is the ultimate unknowable, a boundary that no technology, no matter how advanced, can cross. The more we discover, the more we are reminded of the infinite unknown. Each new discovery opens up more questions, not only about the past, but about the future. Webb's findings have shown us that the universe is constantly changing, but its future is shaped by forces we still don't fully understand. Dark energy is pushing the universe apart, and dark matter is shaping its structure. But what does this mean for the long-term fate of the cosmos? Will the universe continue to expand forever, eventually becoming a cold, desolate void, with galaxies drifting further and further apart? Or will some unknown force come into play to reshape the universe in ways we cannot predict? This realization brings with it a deeper philosophical question. What is the ultimate purpose of cosmic exploration? If we can never fully observe or understand the entire universe, why continue? What are we hoping to achieve when the universe is so vast and in many ways unknowable? The answer lies not in finding the final answer, but in the journey itself. The search for knowledge is an endless pursuit, driven by curiosity and the desire to understand our place in the cosmos. As Webb continues to reveal the universe's secrets, we are reminded that the pursuit of knowledge is not just about reaching the end of the road. It is about embracing the mystery and the journey of discovery. The universe will always be full of unknowns, but that doesn't mean our exploration is futile. Every new discovery, every piece of the puzzle we uncover, brings us closer to understanding the universe's grand design, its origins, and its future. Even as we approach the cosmic horizon, we must continue to ask the big questions. How did the universe begin? How did galaxies form so quickly? What is the fate of the universe? The answers we seek may never be fully within our reach, but the process of exploring the unknown is what defines us as a species. Through telescopes like Webb, we have peered into the past, glimpsing the birth of galaxies, the formation of stars, and the hidden forces that govern the cosmos. We have discovered that the universe is far more complex, dynamic, and interconnected than we could have ever imagined. And as Webb continues to push the boundaries of observation, we must remember that the mystery of the universe is not something to fear. It is something to embrace. The discoveries of Webb are only the beginning. There is so much more to uncover, and while we may never see everything the universe has to offer, we must continue to explore, continue to ask, and continue to seek the truth. The universe is not a place of fixed limits, but one of infinite possibilities, where every answer leads to new questions, and every discovery opens up new avenues for exploration. As the James Webb Space Telescope continues to unlock the secrets of the universe, it has brought us closer to understanding the immense complexity of cosmic evolution. Yet the more we discover, the more we find ourselves standing at the edge of a deep, uncharted ocean of knowledge. The cosmic horizon, which once seemed like a far-off boundary, has become a constant reminder of how little we truly know about the vastness of the universe. This realization, however, does not dampen our curiosity. It fuels it. Webb has provided us with the first real glimpse into the early universe, revealing galaxies that formed when the universe was still in its infancy. These galaxies, once thought to be faint and primitive, are instead massive, bright, and complex, already exhibiting traits that were not expected for such young systems. The findings have forced us to rethink our understanding of the timeline of cosmic evolution. What was once thought to be a slow, gradual process of star formation and galaxy building has turned out to be an explosive acceleration, with galaxies forming, merging, and growing at an unprecedented pace. But as we look deeper into the universe and discover more about its past, we realize that time itself is a more elusive concept than we ever imagined. Webb's ability to peer back in time and observe the light emitted by galaxies that formed billions of years ago is a powerful tool for understanding cosmic history. However, as we look farther into the past, we are reminded of the limits of this method. Every observation Webb makes is a snapshot of a moment in time, a piece of history captured through the stretched light traveling toward us. The very fact that we can only observe ancient light that has traveled for billions of years, is a testament to the passage of time and the expansion of space. As the universe grows older, it is not simply expanding outward, it is expanding faster. And this acceleration has profound implications for our understanding of the future. One of the key insights Webb provides is the role of dark energy, the mysterious force that is driving the universe's accelerated expansion. The existence of dark energy has been a subject of great debate among scientists, but Webb has helped to confirm that it is indeed the driving force behind the rapid expansion of the cosmos. As space stretches and expands, galaxies are being carried farther and farther apart, pushing the cosmic horizon ever outward. This process is accelerating with time, and it seems that dark energy is not just a temporary force, it is a permanent, foundational aspect of the universe's evolution. But with this knowledge comes a sobering realization. If dark energy continues to drive the universe apart, then there is a limit to the amount of the universe that we will ever be able to observe. As galaxies slip beyond our observational reach, we will be left with only a shrinking number of galaxies to study, eventually leading to a future where the universe feels increasingly empty. This scenario raises a profound question. What does it mean to be part of a universe that is forever expanding, yet also forever contracting in terms of what we can see and understand? The expansion of space is not just a concept we encounter in theoretical physics. It is a real phenomenon that is reshaping the very fabric of the universe. Light, as it travels across the vast distances of space, is being stretched by this expansion. This effect, known as redshift, means that the farther light travels, the more its wavelength is elongated, pushing it toward the infrared part of the spectrum. This is why the early universe, which was once detectable in visible light, is now only observable in infrared wavelengths. Webb's ability to detect this stretched light allows it to look back into the ancient past, revealing the first galaxies and stars that formed when the universe was still very young. But as Webb peers farther and farther into the past, we are faced with a paradox. The older the light, the more it is stretched, and the harder it becomes to study. The farther back we look, the more faint and diluted the light becomes, until it reaches a point where it is no longer detectable. The farther we look into the distant past, the more inaccessible the universe becomes. This is a fundamental limit that no telescope, no matter how advanced, can overcome. The universe is not just expanding, it is becoming less observable with time, a fact that challenges our very understanding of cosmic exploration. This tension between our desire to understand the universe and the limits imposed by space-time itself is what makes cosmic exploration so fascinating and so frustrating. We are standing at the edge of an ever-expanding horizon, always on the verge of discovering something new, yet aware that most of the universe will always remain beyond our reach. The more we learn, the more we realize how much we don't know. And perhaps that is what makes the quest for knowledge so compelling. The acknowledgement that the universe is infinitely more complex than we can ever comprehend, and that our pursuit of answers will never be fully satisfied. But even within this vast, unknowable cosmos, Webb's discoveries have offered us something remarkable. A glimpse into the universe's early stages, a glimpse that was once thought to be unattainable. Webb has shown us that the universe is not a static, unchanging place. It is a dynamic, ever-evolving system that is full of life, energy, and mystery. The galaxies it has uncovered are not just static objects. They are active, vibrant, and alive with creation, each one a testament to the incredible forces shaping the universe. Despite the limitations imposed by the cosmic horizon, Webb's discoveries provide us with a clearer understanding of how the universe has evolved, how galaxies have formed and grown, and how stars are born and die. These revelations are shaping the future of cosmic science, offering new insights into the nature of dark matter, the mysteries of black holes, and the role of dark energy in the fate of the universe. And even though there is so much we cannot observe, these discoveries have already transformed our understanding of the cosmos. The more we learn, the more we realize how much bigger and more connected the universe is than we ever imagined. We are just beginning to understand the forces that govern it, and yet there is so much more out there waiting to be discovered. As we continue to push the boundaries of our understanding with the James Webb Space Telescope, one thing becomes ever clearer. The universe is not just vast. It is profoundly isolating. Webb's observations have shown us a universe that is dynamic, vibrant and full of activity. But it has also revealed a universe that is in the process of splitting apart. The universe is expanding, but it's expanding in a way that is not just making it larger, it is making it more inaccessible with each passing moment. The concept of the cosmic horizon, the point beyond which we cannot observe, is not just a limitation of technology or distance. It is a fundamental feature of the universe's structure. As dark energy continues to drive the accelerated expansion of space, the galaxies that are visible to us today will slowly drift beyond the reach of our telescopes. Over time, their light will be stretched and diluted until it becomes undetectable. The farther away a galaxy is, the more its light is redshifted, shifting it beyond the wavelengths Webb is capable of detecting. This cosmic isolation means that eventually, the universe will become a lonely place, with only the most nearby galaxies remaining within our view. This inevitable isolation of the cosmos presents a sobering reality. The universe, while endlessly expanding, is also growing more empty as it expands. We are witnessing the unraveling of the vast cosmic web that holds galaxies, clusters, and structures together. The structures we see today, the clusters of galaxies that are so intricately connected, will eventually become islands in a sea of emptiness, isolated from one another by the growing gaps between them. Webb's observations have made it clear that the universe is not just vast in size, but also in time. The light that Webb captures has traveled across the cosmos for billions of years, offering us glimpses of a universe that no longer exists. These glimpses are frozen moments in time, and as the universe continues to expand, even the light from these distant galaxies will fade, leaving us with fewer and fewer windows into the universe's past. The time gap between what we observe today and what is actually happening in the universe is growing larger by the day, leaving us with an incomplete picture of the cosmos. Yet, despite this overwhelming sense of isolation, Webb's discoveries are forcing us to confront the idea that dark matter and dark energy are the true architects of the universe's structure. These invisible forces, though undetectable by our traditional means, are the ones responsible for shaping the universe's cosmic web. Dark matter, which makes up about 85% of the matter in the universe, has been revealed as the hidden scaffolding of the universe. Its gravitational pull is what holds galaxies together and shapes the large-scale structure of the cosmos. Without dark matter, galaxies and clusters would have never formed in the way we observe them today. Even more mysterious is dark energy, the force that is driving the accelerating expansion of the universe. Unlike dark matter, which is visible only through its gravitational effects, dark energy is an unknown force that permeates all of space and drives galaxies apart. Its exact nature is still one of the greatest unsolved mysteries in cosmology, but Webb's findings have confirmed its existence by observing the accelerated expansion of the universe, which is clearly linked to this invisible force. Together, dark matter and dark energy create a delicate balance between gravity and expansion. On large scales, gravity draws matter together, creating galaxies and clusters, while dark energy pushes everything apart, ensuring that galaxies move farther and farther away from one another. It is this cosmic tug-of-war that determines the evolution of the universe. Gravity, which governs how galaxies and stars form, is continually at odds with dark energy, which is pulling everything apart. This dynamic balance shapes the universe's structure, from the formation of galaxies to the very expansion of space itself. What Webb has shown us, through its ability to peer into the distant past, is that this balance is not static, it is evolving. The forces of dark matter and dark energy are constantly in flux, with dark energy growing stronger over time and dark matter remaining a constant invisible presence. This interplay between forces has defined the universe's evolution, and it will continue to shape its fate. But as we observe this cosmic dance, we must ask, what is the future of the universe in this cosmic tug-of-war? If dark energy continues to drive the universe's accelerating expansion, galaxies will continue to move farther apart, eventually slipping beyond our observational reach. Over time, the cosmic web will unravel, and the universe will become a more isolated place, with galaxies becoming increasingly disconnected. The light from galaxies that were once visible to us will eventually fade, leaving us with a shrinking view of the universe. This scenario raises the specter of what some have called the Big Freeze, a future where the universe becomes an expanding void, with galaxies isolated from one another and stars burning out over the course of trillions of years. In this future, the universe will become cold and dark, with little interaction between galaxies and no new stars forming. The universe will have reached the end of its story, with its structures and galaxies drifting apart forever. But even this distant future is still a long way off, and the mysteries of the universe are far from over. While the observable universe is expanding and shrinking with time, the potential for discovery is ever present. Webb's revelations are only the beginning of a much larger journey. As we continue to observe the universe and uncover its deepest secrets, we will be forced to redefine our place in it. The realization that the universe is not just expanding, but also slipping away from us, is a humbling one. But it also drives us to continue asking questions and seeking answers. For now, the universe remains full of wonders and mysteries, and with Webb's continuing discoveries, we are on the brink of unlocking even more of its secrets. The question is not whether we will ever fully understand the universe, but how much we can learn before the cosmic horizon stretches beyond our reach. As we journey deeper into the mysteries revealed by the James Webb Space Telescope, one thing becomes evident. The more we uncover, the more we are confronted with the immensity and mystery of the universe. Webb's unprecedented capabilities allow us to peer into the distant past, unlocking the secrets of galaxies, stars, and cosmic structures that formed billions of years ago. Yet, despite all we've learned, the true extent of the universe, its size, its complexity, and its future, remains fundamentally unknowable. The discoveries made by Webb have fundamentally shifted our understanding of the cosmos. Galaxies that formed in the universe's infancy, only a few 100 million years after the Big Bang, have revealed a cosmos that was much more active and complex than we had ever imagined. These early galaxies, once thought to be dim and fragile, are massive, bright, and forming stars at rates previously thought impossible so soon after the birth of the universe. This discovery alone challenges our assumptions about the evolution of galaxies, throwing long-standing models into disarray and forcing us to reconsider how quickly complexity can emerge from the chaos of the early universe. However, the more Webb reveals, the more we realize that for every answer we find, there are still countless more questions. What Webb has shown us is just a tiny fraction of the vast, dynamic universe. The observable universe, the portion of space for which light has had time to reach us, is limited not just by distance, but by the expansion of space itself. As dark energy continues to stretch the universe, vast regions of space will slip beyond the reach of our instruments. Galaxies, stars, and black holes that we can observe today will eventually fade from view as their light is stretched beyond detection. And in time, we will be left with only the most local portions of the universe, isolated and increasingly distant from the rest of existence. This inevitable isolation of the universe is a humbling reminder of how much we can never know. The cosmic horizon represents the boundary of our observational capabilities, and as the universe expands, that boundary stretches farther, pushing the unseen regions of space further and further away. The light from distant galaxies and stars, which has traveled across vast distances to reach us, will eventually be lost to time. In the far future, the observable universe will shrink, and the cosmos will seem increasingly sparse. The cosmic web, the intricate network of galaxies, dark matter, and gas that Webb has revealed, will continue to grow, but much of it will become unobservable, fading into the unseen reaches of space. While this realization might seem like a profound limit on our understanding, it also compels us to look at the universe with a sense of awe and humility. The more we learn, the more we realize that our understanding is but a glimpse into something far larger and more complex than we can ever fully comprehend. Webb's discoveries are pushing the boundaries of our knowledge, but they are also forcing us to accept that the universe is far more unfathomable than we ever thought possible. Yet, even within this cosmic mystery, Webb's data reveals something remarkable. The universe is not random. Despite its vastness and complexity, there is an undeniable order to the cosmos. Dark matter, which makes up about 85% of the matter in the universe, has been revealed to play a pivotal role in structuring the universe. It forms the invisible framework that holds galaxies and clusters together. Without dark matter, galaxies would never have formed in the way we observe them today. Webb's findings show that dark matter has shaped the large-scale structure of the universe, creating the cosmic web that we now understand to be the very scaffolding of the cosmos. Even more fascinating is the revelation that dark energy is not just a passive force. It is an active player in the universe's future, driving its accelerated expansion and shaping the cosmic timeline. The realization that dark energy is responsible for the universe's rapid expansion has forced scientists to reconsider many of their assumptions about the fate of the cosmos. If dark energy continues to accelerate the expansion of space, the universe will continue to grow larger, leaving galaxies and clusters isolated in an ever-expanding void. But as we look toward the future, we are left with profound questions about the ultimate fate of the universe. Will dark energy continue to drive the cosmos apart indefinitely, leading to a future where galaxies are scattered and isolated? Or is there something else at play, forces we don't yet understand, that will alter the course of cosmic evolution? Webb's findings have opened the door to these possibilities, and yet the answers remain elusive. One possibility is the Big Freeze, where the universe continues to expand at an accelerating rate, ultimately leaving all galaxies isolated from one another. In this scenario, stars would burn out, galaxies would drift apart, and the universe would become a cold, dark, and empty place, where the light from distant galaxies is lost forever. This is one possible outcome if dark energy continues to dominate the universe's expansion. Yet there are still other possibilities. Could the expansion of space slow down? Could it even reverse, causing the universe to collapse inward in a big crunch? Could dark energy itself evolve, becoming weaker or stronger, altering the universe's destiny in ways we can't yet predict? For now, these possibilities remain speculative, and Webb's discoveries have only deepened the mystery. What is clear, however, is that the universe is not static. It is an evolving dynamic system driven by forces we still don't fully understand. The cosmic web, which Webb has revealed in unprecedented detail, is a reminder that the universe is interconnected in ways that go beyond our ability to see or measure. The galaxies, stars, and clusters we observe today are but a snapshot in the long journey of cosmic evolution. And yet, the more we observe, the more we realize how much of the universe remains hidden, forever beyond our reach. As we look toward the future, the challenge is not just about observing the universe, but about embracing the limits of what we can know. The universe, with all its wonders and mysteries, is far beyond our full comprehension, but that doesn't make our exploration any less meaningful. Instead, it challenges us to continue searching, to keep asking questions, and to accept that the journey, the pursuit of knowledge, is as important as the answers we find. The true beauty of cosmic exploration lies not in reaching the end of the journey, but in the quest itself. In our willingness to confront the unknown, to ask the big questions, and to embrace the infinite complexity of the universe, even if we can never fully unravel its mysteries. As we continue to reflect on the discoveries made by the James Webb Space Telescope, one undeniable truth emerges: the universe is far more intricate, dynamic, and unfathomable than we ever imagined. With each revelation, we are forced to confront the sheer vastness of space, not just in terms of distance, but in the incredible complexity of its structure and forces. The universe is not simply a collection of stars and galaxies, as we once thought, but a vast interconnected web, shaped by invisible forces like dark matter and dark energy. What Webb has unveiled is a universe that is in motion, evolving, and driven by forces that, at present, remain largely mysterious. The more we observe, the more we realize that the universe's evolution is governed by a balance of competing forces. Forces that we cannot fully understand, even with the most advanced tools at our disposal. But this lack of complete understanding should not discourage us. Instead, it should drive us to explore further, to push the limits of our knowledge, and to accept that the journey of exploration is as important as the destination. Webb's discoveries have radically shifted our understanding of the early universe. The galaxies we observe today are not the fragile, slowly forming entities that we once believed them to be. Instead, Webb has shown us galaxies that are already massive, bright, and actively forming stars at astonishing rates, barely a few 100 million years after the Big Bang. These galaxies are far more complex than anything we expected, challenging our models of how galaxies and stars should evolve over cosmic time. What Webb has shown us is that the universe was never a slow, steady process. It was a rapidly accelerating journey toward complexity. The early universe was far more energetic and efficient than we ever thought. Galaxies formed quickly, and stars ignited at rates much higher than expected for such young systems. This accelerated formation of galaxies raises an important question. Why was the universe so efficient in its early stages? Why did it rush toward complexity rather than slowly building it over billions of years? One answer may lie in the behavior of dark matter. This invisible substance, which makes up the majority of the universe's mass, played a pivotal role in structuring the early cosmos. Webb's observations of the cosmic web, the vast network of filaments of dark matter and gas that connects galaxies across the universe, reveal that these filaments were already well established in the early universe, long before the formation of stars and galaxies. Dark matter acted as a scaffolding for the universe, providing a structure within which galaxies could form and grow rapidly. The role of dark matter in the cosmic web is not just one of support. It actively guides the flow of matter, shaping the universe's large-scale structure. As Webb has shown, these dark matter filaments direct the movement of gas and galaxies, creating clusters and voids, and ultimately driving the evolution of the cosmos. What Webb's findings have highlighted is the invisible hand of dark matter in shaping the universe's structure, a force that operates on a scale far beyond our everyday experience, and one that we still do not fully understand. In addition to dark matter, dark energy plays an equally important role in the universe's evolution. This mysterious force is driving the accelerated expansion of space, pushing galaxies farther apart and reshaping the structure of the universe. Dark energy's presence has been confirmed by Webb's ability to measure the universe's expansion, but its exact nature remains elusive. Some scientists speculate that dark energy is a form of energy inherent to empty space itself, while others propose that it could be a property of gravity that we don't yet fully understand. Whatever its true nature, dark energy is an essential component of the cosmic puzzle, driving the universe's expansion and shaping its long-term fate. The interplay between dark matter and dark energy is what defines the universe's evolution. Dark matter, which pulls matter together through gravity, creates the structure of the cosmos, the clusters of galaxies, the vast filaments, and the cosmic web. Meanwhile, dark energy pushes the universe apart, accelerating the expansion and causing galaxies to drift farther from one another. Together, these forces shape the grand design of the cosmos, creating a universe that is at once ordered and chaotic, expanding and contracting. Yet, for all the knowledge Webb has given us, there is still much we do not understand about these dark forces. Dark matter remains invisible, detectable only through its gravitational influence on visible matter. It does not interact with light or other forms of electromagnetic radiation, making it impossible to study directly. The nature of dark energy is even more mysterious, and its influence on the future of the universe remains uncertain. Will dark energy continue to accelerate the expansion of the universe indefinitely, or will it eventually fade away? These questions remain unanswered, and Webb's findings have only deepened the mystery. But perhaps the greatest mystery revealed by Webb is the universe's future. If dark energy continues to drive the accelerating expansion, then galaxies will continue to move farther apart. Eventually, the light from these galaxies will be stretched beyond detection, and the universe will appear increasingly empty. Stars will burn out, galaxies will drift apart, and the universe will grow ever colder and darker. This big freeze scenario suggests a future in which the universe becomes a lonely, isolated place, with only a handful of galaxies remaining in contact with each other. Alternatively, if dark energy weakens or changes over time, the expansion of the universe could slow, and gravity could once again take control. This could lead to a big crunch, where the universe collapses in on itself, reversing the expansion that began with the Big Bang. Another possibility is that the universe could enter a phase of oscillation, where it expands and contracts in a cycle, perhaps endlessly. These scenarios remain speculative, and Webb's findings do not provide answers. But they do force us to confront the inevitability of the universe's fate. What is clear is that cosmic exploration has only just begun. Webb has provided us with a deeper understanding of the universe's structure, the forces shaping its evolution, and the mysteries of dark matter and dark energy. But with these discoveries comes the realization that the universe is vast beyond comprehension, and that much of it will forever remain out of our reach. The cosmic horizon is not just a boundary of space, it is a boundary of knowledge, a reminder that the more we learn, the more we must confront the limits of our understanding. As we look toward the future, we must embrace the unknown. The universe is far from fully understood, and as our technology continues to improve, we will no doubt uncover even more profound mysteries. But for now, Webb has opened our eyes to the complexity of the cosmos, revealing a universe that is not static, but constantly evolving under the influence of invisible forces. Dark matter, dark energy, and the cosmic web are shaping the universe's destiny, and our place within it is still unfolding. As we reach the final stages of this exploration, we are left with one overarching realization. The universe is a place of infinite complexity, and no matter how far we look, we will never be able to fully comprehend its vastness. The discoveries made by the James Webb Space Telescope have shown us a universe that is actively evolving, shaped by forces we can neither see nor touch, governed by laws and dynamics that challenge our deepest assumptions. Webb has pushed the boundaries of human observation like never before, revealing galaxies that formed when the universe was still in its youth. These galaxies are not the fragile, dim systems we once imagined. They are bright, massive, and bursting with activity, forming stars at rates we never thought possible for such early systems. They are a testament to the acceleration of cosmic complexity, where the universe didn't slowly evolve, but instead rushed towards structure and formation. This acceleration of the universe's development forces us to reconsider everything we thought we knew about cosmic time. For years, we believed that galaxies and stars formed gradually, over long stretches of time. But Webb's findings have shown us that the universe was far more efficient in its early days, with galaxies coming together quickly and forming stars at an astonishing rate. The universe didn't take its time. It moved at lightning speed, creating massive galaxies and stars in the blink of an eye, in cosmic terms. Yet, as we marvel at these discoveries, we are also confronted with the limits of our exploration. Even with Webb's advanced technology, there are regions of the universe that will forever remain beyond our reach. The cosmic horizon is a boundary defined by space's expansion, a point beyond which we cannot observe. The light from distant galaxies will continue to stretch and redshift until it is no longer detectable by any telescope. Webb, for all its brilliance, cannot reach beyond this horizon. And the further we look into the past, the more we realize how incomplete our understanding is. This realization forces us to ask, what is the true nature of the universe? Is it just a collection of galaxies, stars, and planets? Or is it a much more interconnected, dynamic system governed by unseen forces like dark matter and dark energy? These forces shape the very structure of the universe, guiding the formation of galaxies and stars, while simultaneously driving the accelerating expansion that is pulling the universe apart. It is the invisible mass that holds the cosmic web together, shaping the large-scale structure of the universe. And yet, we still do not know what dark matter is made of, nor how it operates on the smallest scales. The mystery remains, and Webb, for all its discoveries, has only deepened our fascination with this elusive substance. In contrast, dark energy, the force that is accelerating the expansion of the universe, is even more enigmatic. We know it exists because we can see its effect on the expansion of space, but we do not understand its true nature. As Webb continues to observe the universe's distant reaches, it is clear that dark energy will play a major role in determining the future of the cosmos. Will the universe continue to expand indefinitely, becoming more isolated and empty over time? Or will dark energy change in ways we cannot yet predict, altering the fate of the universe in ways that no one has imagined? The future of the universe is unknowable, and that truth is perhaps the most humbling revelation of all. As we observe the galaxies and stars that populated the early universe, we are reminded that these objects no longer exist as we see them. They are snapshots of moments that have passed. The universe is not static. It is always in motion, always evolving. The galaxies Webb observes today were not static objects in the past. They were part of an ongoing story, one that is still being written. This dynamic nature of the universe forces us to accept that our understanding will always be limited. No matter how much we discover, the universe will always hold secrets just beyond our reach. It is an uncomfortable truth, but it is also what makes the pursuit of cosmic knowledge so profound. The universe is not something to be fully understood. It is a mystery that we must learn to live with, a mystery that will continue to inspire generations of explorers, scientists, and dreamers to seek answers to questions that may never be fully answered. Yet, despite the limitations we face, Webb has already changed the way we see the cosmos. It has provided us with a glimpse into the early universe, showing us galaxies and stars that formed when the universe was still young, full of potential. It has revealed the complex interplay of dark matter and dark energy, forces that govern the structure and evolution of the universe. And it has shown us that, despite the vastness of space, the universe is interconnected, a network of forces and objects that are constantly in motion, changing and evolving. And that, in the end, is the greatest gift of all. The universe, for all its incomprehensible scale and mysterious forces, is a source of endless wonder. Webb has shown us that the cosmos is not a static, unchanging thing, but a living, breathing entity, full of energy, activity, and infinite possibility. We may never understand it all, but the journey of discovery, the search for meaning and understanding, is what makes us human.